Hello everyone. Today our group will going to present our assignment with the title Synthesis and Characterization of Polyethylene Emeraldine Salt. And this is our group members. Polyethylene is a unique pi-conjugated conducting polymer that possesses high electrical conductivity. This conductivity is made possible by its pi-conjugated backbone, which enable electron delocalization and redox activity throughout the polymer chain. Structurally, it consists of repeating aniline units linked via amine groups, forming a system that can readily transfer charges. Polyaniline is distinguished by its ability to exist in multiple oxidation states, specifically leucomeradine, emeraldine, and pronigranilin. Our focus is on the emeraldine salt form, which is the most conductive state and is easily identified by its characteristic green color. It is highly valuable in material science because its electrical properties are tunable through a process called protonic doping. Polyethylene has several applications including corrosion protection, chemical sensor, and energy storage. And this is our objective.
Next, I will explain the sample description. The sample used in this study is polyaniline amarylline salts, or PANI-ES, which is intrinsically conducting polymer. It has a conjugated backbone made an alternating benzoate and quinoid units, allowing charge delocalization and electrical conductivity. The polymer was synthesized under acidic conditions, producing a green color that indicates successful protonic doping. The sample was prepared in solution, film, and powder forms to support different types of characterization. For the experimental methodology, polyaniline was synthesized using chemical oxidative polymerization of aniline with hydrochloric acid and ammonium persulfate. The polymer was then prepared in different physical forms, including a film coated on an etched zinc substrate. FTIR was used to study the chemical structure, FISM to observe surface morphology, and EDX to confirm elemental composition.
FTIR spectroscopy was used as the main chemical characterization technique to confirm the structure of polyaniline emeraldine salts. In the presence of benzonoid and quinoid ring stretching bands between 1500 and 1600 inverse centimeters indicates the emeraldine oxidation state. CN stretching and protonated amine bands further confirm successful protonic doping and formation of the emeraldine salts. FASM EDX was used to analyze the surface morphology and elemental composition of polyaniline emeraldine salts. FASM provides high-resolution images of surface texture, particle distribution, and film uniformity, while EDX gives qualitative elemental information related to the polymer and dopant species. Any zinc detected originates from the substrate and not the polymer itself.
First, this slide shows the FAIR result used to confirm the chemical structure and protonation of PANI-ES. The broadband at around 3,200 to 3,400 cm correspond to enhanced stretching indicating protonated amine group. The presence of both quinoid and benzonoid ring stretching band at approximately 1,516 and 1,419 cm confirm that the polymer is in the emeraldine oxidation state. The CN stretching band near 1,300 cm and the protonated enhanced positive direction around 1,000 to 1,100 cm further confirm successful acid doping. Together, these features verify the formation of proton-doped PANI-ES. Next, the physics image shows the surface morphology of the PANI-ES field at different magnification. At low magnification, the field appears continuous but round, indicating successful coating on the substrate. At higher magnification, wrinkle and flat-like structure form an interconnected network which arise from polymer chain aggregation and pi-pi stacking interaction. The essence or subcrystalline feature indicating an amorphous to semi-order structure, which is typical for acid-doped polyaniline and beneficial for charge transport. Lastly, EDS analysis was used to support the elemental composition of the PANI-ES field. The spectrum showed the minimum carbon and oxygen pin from the polymer backbone along with a clear sulfur signal originating from the acid dopant. Elemental mapping confirmed that carbon, oxygen, and sulfur are uniformly distributed across the field surface, indicating homogeneous doping and coating. Although EDS cannot detect proton directly, the present and uniform distribution of sulfur strongly support the formation of polyaniline in its emeraldine source form.
For the integrated discussion, FTIR analysis confirmed that the emeraldine oxidation state through characteristic benzonoid and quinoid bands indicating successful protonic doping. FISM observations revealed a rough, wrinkled, and interconnected surface morphology, which is typical of chemically synthesized doped polyaniline. EDX analysis also detected sulfur from the acidic dopant and showed uniform elemental distribution across the polymer film. Overall, the agreement between chemical morphology and elemental analysis confirms the successful formation of polyaniline emeraldine salt. So in conclusion, polyaniline emeraldine salt was successfully synthesized via chemical oxidative polymerization under acidic conditions. FTIR spectroscopy also verified the emeraldine salt structure and emphatic protonic doping of the polymer backbone. And also, FESAM and EDX analysis supported the formation of the dope conducting polymer with characteristic morphology and sulfur incorporation. In conclusion, the synthesis method was effective and all objectives of the study were successfully achieved.